Okay, we're back after that little break, and so now what we're going to do is we're going to develop a sufficient condition for a point to be a maximizer or a minimizer of a function. And again, it'll be local maximum or local minimum for today. And so we're going to say that, again, that X is an open set in RL, and we'll assume that f, real valued function on x, is a C2 function. And of course that just means that each partial derivative function, second partial derivative function I should have said, of course this depends on x, is a continuous function. Let's say it's a continuous function. So all the second partial derivatives exist, and they're all continuous functions of the point in the domain at which we evaluate them. And let's do one other thing here. Let's point out that we're going to use, as we've done before, h of x as the Hessian matrix, and let's just, so that's the matrix we call the Hessian matrix, which is the matrix of second partial derivatives. So let's just say that's the matrix consisting of the second partial derivatives evaluated at x. And again, most often we leave off the argument x when we're writing these second partials, but I put it in here just to emphasize that it's implicitly it's there. Second partial derivative, just like the first partial derivatives, they depend on the point at which we're evaluating those derivatives. So what we're going to do now is we're going to develop a sufficient condition for x bar to guarantee that x bar is a local maximum. And in fact, here I'm actually going to we're actually going to do our sufficient condition that guarantees that x bar is a local minimum for reasons that may become clear as we do this. So let's say theorem if the gradient of f at x bar is the zero vector, all the partial derivatives are zero. So first of all, we already know that this is a necessary condition for x bar to be a local maximum. And so if we're going to get a sufficient condition for x bar to be a local maximum, it's going to have to include this, because if this isn't satisfied, any additional conditions are going to be useless because it won't be a local maximum or minimum. So if the gradient is zero and the Hessian matrix evaluated at x bar is negative definite. If that's a negative definite matrix, and of course the Hessian matrix is symmetric because the fact that the second derivative functions are continuous means that the second partial of f with respect to xi and then xj is the same as the second partial with respect to xj and then xi. So this is for any x, this is a symmetric matrix. And so we're saying that this symmetric matrix, the Hessian, this matrix of second partial derivatives of f, is at x bar has got to be negative definite. So if it's negative definite, then x bar is a local minimum. Oh, I'm sorry, I said negative definite. let's make that positive definite, because I do want to work with this being a minimum. So let's, in fact, that was really the main reason I wanted to do this, was I want to have this be positive definite. Then x bar is a local minimum. In fact, it's a strict local minimum. So let me make that clear here. Then x bar is a strict local minimum of f. A proof. We're going to, again, just like we did for our necessary condition, I'm going to come over here and give a proof for the case L equals 1. So where we have a real function, the domain is just a one-dimensional, is just the reals. And let's see if we're going to, I think that I'm going to take this off so that we have some room to do that. So I'll take a moment to take this off, and then we'll be right back. Okay, we've got some space now to give our L equals 1 proof, and then we'll, after we do that, we'll come back and we'll give the kind of analogous proof for the general case. So over here we will do proof for L equals 1. So let's start off by writing how much the y variable is going to change. I'm going to write that as capital F of delta x, as we have done before when we were talking about Taylor approximations, which of course is what we're going to use here. And so this, we've said, would be f at x bar plus delta x minus f at x bar. And now we want to make sure that x bar is a local minimum here. So let's actually write down our Taylor second degree polynomial approximation to this function. And so this is going to be f prime at x bar times delta x plus 1/2 f double prime at x bar delta x squared plus a remainder term or error term, which will be R2 of delta x, R2 because it's the remainder term for the second degree polynomial. And of course, notice I've left out the 0 degree term because that's over on the left-hand side, f of x bar. So I've taken that over to the left-hand side for this difference here. And so this is the exact change in y. This much here is an approximation, and then this is the residual or error or remainder. And what we know about this is that this R2 function of delta, yes, that's okay. So what I want to do next is I want to divide everything by delta x squared. In fact, let me even put here that this one thing we know about this R2 is that, and I'm going to do that down here, the limit as delta x goes to 0 of 1 over the square of delta x times R2 of delta x is 0. So that's one thing we know about this remainder term, is that its the limit of that term, of that function, if you like, when it's divided by delta x squared is 0. So that we've developed earlier when we were talking about the Taylor polynomial approximation. So what I'm going to do now is I'm going to divide both sides of this by delta x squared. So that means I have over here, I have 1 over delta x squared times f of delta x here. That is going to be equal to, well, first off, notice that the derivative at x bar is 0. Here I've got it as the gradient, but in the case that L is 1, this is just the derivative of f at x bar, and that has to be 0. So if this is 0, this whole term here drops out. That's 0. So this is now 1/2 times the second derivative times delta x squared, but I've divided by delta x squared, so I've just got here now just 1/2 f double prime at x bar. Almost wrote delta x in there. And then over here I've got plus 1 over delta x squared R2 of delta x. Let's call this, it's a different color here. Let's call this just R of delta x. A little simpler than this here. And what we know is that the limit as delta x goes to 0 of this R of delta x function is 0. So the limit of this as delta x goes to 0 is 0. And what's this? Well, this is just some positive number. Because we've said the matrix of second partial derivatives is positive definite, but in the case of L equals 1, this is just the second derivative of f. So the second derivative of f, evaluated at x bar, is positive, and so this is some positive number. And I've just written it beta, just to emphasize it's a fixed number. It doesn't depend on delta x. Of course, it depends on the x bar where we are, but it doesn't depend on delta x like this does and like this does. So this function of delta x over here is this numbered beta plus this function here, which has a limit of 0 as delta x gets small. And so what this tells me is that for this number small enough, the let's just say that for delta x small enough, we have the sign of f of delta x delta x is not 0. The square of delta x is positive. So the sign of the left-hand side, of course, has to be the same as the sign of the right-hand side. The sign of the left-hand side is just the sign of f of delta x. The sign of the right-hand side, if r of delta x gets smaller than beta in absolute value, as it will do if we make delta x small enough, this will be dominated by beta, and we've assumed that beta is positive, so this is going to say this is equal to the sine of beta, or the sine of f double prime of x. And so if the sine of this is the same as the sine of this, if this is positive, then f of delta x is positive. And so that says that beta positive, that gives us f at x bar plus delta x is bigger than f at x bar. Strictly larger, because the sign of this is strictly positive. Beta is positive. This gets smaller than beta. So the sign of this is strictly positive. So f of x bar plus delta x is larger than x bar for every delta x small enough, for every delta x in some neighborhood of 0, just as it says down here. So, and of course, that guarantees that x bar is a strict local minimum of the function, because when I move away from x bar, the function gets larger. The value of the function gets larger. And actually, you can see that the proof here actually works for showing that x bar is a strict local maximum if the second derivative is negative. Because if the second derivative is negative, then the sign of this is the sign of beta. If beta is negative, this is negative, and this is less than this. So x bar would be a local maximizer, a strict local maximizer of f. So this completes the proof of this theorem for the case L equals 1. It's quite simple and relies on the fact that in the second degree Taylor approximation, where the second degree quadratic term has the second derivative as the coefficient, we also have our remainder term going to 0, well, when divided by delta x squared, going to 0. So that's a key part of the proof. So let's now go back over to the general case for any L and see if we can use what we did here to figure out how to prove this over here. So let's start the same way. Let's say that delta y is capital F of delta x, and that's f of x bar plus delta x minus f of x bar. That is going to be equal to, now the first degree term, the linear term, is the gradient of f at x bar times delta x. So that's a vector and that's a vector. But of course what we get is a number, plus 1/2 delta x h of x bar, the Hessian matrix, times delta x. Again, I'm ignoring the issue of transposes of vectors to make the row vectors match up with column vectors and so on. Remember when we talked about quadratic forms, I just wrote this for, here's the matrix of the quadratic form, and here's the variable that goes into the quadratic form. And so then we of course also have, just as over here, we have R2 of delta x. Well, we can't quite do the same thing as we did over here because, well, let's first notice that this part is 0. Because the gradient is the 0 vector. So the 0 vector times any vector here is going to be 0. So that's going to drop out. And in fact, let me even go a little farther. Here I divided by delta x squared. Well, I can't do that over here because here delta x was a number. Here delta x is a vector. I can't take the vector squared. But what I can do is I can divide by the norm of the vector. And I'm going to, of course, divide by the square of the norm of the vector, make it analogous to this. And I'm also going to divide by the square of the norm of the vector because that's what's going to make this go to 0. So let's go back over here and write down the analog of this statement here in the multidimensional case. So that's going to be that the limit as delta x goes to 0 of 1 over the norm of delta x squared, R2 of delta x is 0. So in the one-dimensional case, the remainder term has this characteristic, has this feature, that when I divide it by delta x squared, that resulting function, which I've called little r of delta x, has 0 as its limit. And over here, it is that since we can't divide by delta x, or delta x squared, what happens over here is that 1 over the norm of delta x squared times r2 of delta x goes to 0. That's what we know about the Taylor, the second degree Taylor approximation to our function capital F of delta x, or this function here. So I'm going to now divide through, just like I did here with delta x squared, I'm going to divide through by norm of delta x squared. So we have 1 over norm delta x squared f of delta x on the left-hand side. And on the right-hand side, this part dropped out. I have 1/2. Well, I'm dividing by norm of delta x squared. So I'm going to divide first. I'm going to take 1 over the norm of delta x as my scalar to multiply delta x by. Then I've got h, x bar. And then on this side, I've got the same thing. 1 over norm of delta x times delta x. So this quadratic form here becomes this quadratic form here because I've divided by the norm of delta x squared, which I could put out in front, but then I can take one of the delta x norms and divide by that, and I have a scalar times delta x, and then I can do the same thing over here. So 1 over delta x squared times this quadratic form is exactly this quadratic form. And of course over here, I'm going to have, and I guess I'm going to have to put this down here to squeeze it onto the screen, I have 1 over norm delta x squared. Whoops, it's not the real numbers. That's just r. R2 of delta x. Again, let me call this, as we did over here, let's call this r of delta x, just to give it a nice shorthand name and to emphasize this whole thing is simply a function of delta x. And so now we have to do a little trick here. A little trick that uses the Weierstrass theorem, actually. So here we see our first use, maybe, of the Weierstrass theorem in actually getting a result that we need. So let's do that by saying, so let's go across here, and let's say this is what we call a lemma, meaning some proposition that isn't kind of a general proposition that we're going to use all the time. It's something we're just going to use within the proof to accomplish the proof we're trying to do. And that's going to be that if S is the set of all, and I'm going to use z's. The z's, I'm going to substitute in this vector for z once we apply this. But I don't want to use x because that could get confused with the x's in here. So if S is the set of all z's, let's say, in RL, such that the norm of z is exactly 1, let's cut this off here, and if Q is a positive definite quadratic form, positive definite quadratic form on RL, then the quadratic form attains a minimum on, do I want this to be a minimum? Let's see here. Yes, a minimum on S. Okay, so let's see what's going on here by drawing a little diagram. So we've said that S is the set of all vectors in RL that have norm exactly 1. So let's draw a picture over here. And let's say this is Z1 and this is Z2. And this is 1 on this axis and 1 on this axis. So this is the unit sphere. And here we're in R2. This is just a special case that we can draw of RL. And so the circle, the unit circle, is the set of all vectors in RL that have norm exactly 1 for the Euclidean norm. Actually, we could do the same thing for any other norm. Suppose I take the max norm. Just like everything else we've done, this is going to be independent of what norm we use. This is just to emphasize that we could do this. We could take the city block norm, and then we'd have a diamond in here. So unit circle, unit square, doesn't make any difference here. In each case, in fact, let's say here, this is all of the z's such that the norm of z is 1. In the Euclidean norm, this is all of the z's such that the norm of z is 1. Max norm, Euclidean norm. Doesn't make any difference. So that's the set S. We have a quadratic form that's positive definite quadratic form in RL. And since it's positive definite, that means that it's got to be strictly positive, not 0, strictly positive on the entire unit circle or unit square. It's got to be positive everywhere on here, right? But it's also the case that S is compact. So let's give a little proof of our lemma. S is compact, closed and bounded, not the interior, it's just the circle, just the square. S is compact, and quadratic forms are all continuous functions. S is compact, Q is continuous, therefore Q, that's it. I mean, apply the Weierstrass theorem and we have Q attains a minimum. And in fact, let's even say this a different way just so that we can apply it up here. So that says that, I mean, it says that Q attains a minimum. Well, no, in fact, let's write that down. So therefore, Q attains a minimum let's say beta on S, and that minimum has to be strictly positive. It can't be 0. Why not? Because if Q was ever 0 on this, it wouldn't be positive definite. If it's positive definite, it's positive everywhere in the space except the origin. And so the origin's not included in this set. So Q attains a minimum, and that minimum has to be positive because it's a positive definite quadratic form. Strictly positive. So actually, the lemma that we wanted here was not just that it attains a minimum, but that beta is strictly positive. So that's what we need here. So let's just come back now to this equation. And so what do we have? This This, whoop, not there, all the way over to here, all the way over to there. So this is a quadratic form, and the variables for the quadratic form are always on the unit circle or the unit square, depending on the norm we're using, because the norm of is just the absolute value of this scalar times the norm of delta x. So this is norm delta x, 1. So this quadratic form, now we're only worried about what happens to the quadratic form on the unit circle or the unit square, right? So we've shown that it has a minimum which is strictly positive, and so this beta now plays the same role as the beta over here that was strictly positive. Here, it was a little trickier to get such a beta. Here, it was just straightforward, because this was a number, and that number we assumed was positive because that was in the assumption of the theorem. Over here, in order to get this expression to be above, bounded away from zero, bounded above zero, so that small delta x's would make this expression smaller than this, we had to kind of go through this little trick here with the Weierstrass theorem to guarantee that there's a beta such that this thing is always greater than or equal to that beta. So what we have then is that for small enough, and we're about out of room down here, I can squeeze this in. For small enough delta x, we have r of delta x is smaller than beta, so we have f of delta x dividing by something squared. So the sign of this is going to be the same as the sign of this, which is positive, because our beta is positive. And if f of delta x is positive, that says, and let me squeeze that in, I guess we'll just stick that in here. F of delta x is positive, well, we just do that over here. It says that f of x bar plus delta x is bigger than f of x bar. So the conclusion, the same conclusion we got over here in the one-dimensional case, says that for all delta x's sufficiently small, f is going to be strictly larger at x bar plus that delta x than it is at x bar, and that says that x bar is a strict local minimum of f. So that gives us a sufficient condition to guarantee that a point is a strict local minimum. It's obvious that the sufficient condition to guarantee we have a strict local maximum is that the Hessian matrix is negative definite. So we now have sufficient conditions that will guarantee that we have a strict local minimum or a strict local maximum. And the sufficient conditions are both first and second order. The first order condition that we have to guarantee that we have a strict local minimum or maximum is that the derivative is zero, the gradient is the zero vector, and then the second order condition, the second derivative condition, is that the matrix of second partial derivatives has to be positive definite for strict local minimum, negative definite for strict local maximum. So I think that is all that I want to do for, I guess we could call it part 2 of our lecture on unconstrained optimization. And we have one more thing that we want to do, so we'll take a break and we'll come back and do that. that is going to be to look at a second order necessary condition for maximization. So we'll take a break, we'll get all this off the screen, and then we'll come back and we'll finish up our analysis of unconstrained optimization. Okay.